definitely I'll always have questions. If I ask you for the definition of temperature, can you answer that? What do you mean by temperature?
Speed at which the molecules are moving.
Man, you did read a lot. Otherwise, you would not have come. Usually, the answer that I hear about temperature is it's the measure of heat in a substance. That's what I hear, which is not correct. Because if you have a glass of water and you have the ocean, which one has more heat? Is it the glass of water or the ocean? That's an easy guess. Which one has more heat?
Ocean.
Definitely the ocean has more heat in it. But the temperature of the glass of water could be higher than the temperature of the ocean. You see what I'm trying to say? Because when you talk about heat, you also have to consider the mass of the substance. There's a lot of mass of water in the ocean, see? So you cannot say that temperature is a measure of heat. Temperature is the mean kinetic energy of molecules in a substance. Temperature is the mean kinetic energy of molecules in a substance. Because you know that in all substances the molecules are moving, right? They're vibrating. They're moving about. The faster they move, the greater the temperature. So actually temperature is a measure of kinetic energy. Is there any temperature at which all molecular motion would stop? Absolute zero. 0 Kelvin. Now at that point, and we've not reached 0 Kelvin. Remember, we got very close. 0 Kelvin is negative 273 degrees Celsius. You know that, right? We got as close as 272.91 degrees Celsius. And that's a very low temperature, you know that. And they're trying, the closer you get, the tougher it is. Because theoretically, the lowest temperature that can be reached is absolute zero. And they've got this far. And now at this temperature, volumes become zero, pressure becomes zero, temperature drops to zero, kinetic energy drops to zero. Everything becomes zero. But now, talking about absolute zero and Kelvin, there are different temperature scales, aren't there? We usually measure in Fahrenheit, but you have heard of Celsius, and then you have Kelvin. But in physics, this could be the most important thing that I'm telling you the whole day. All temperatures must be measured in Kelvin and nothing else. Celsius might work, but to be on the safe side, always change into Kelvin. You are safe. All right. So having said that, we have to look at the three temperature scales and compare them. Look and see how they are and how they have set up that way. Like I said, temperature is the average kinetic energy of molecules. These are the three temperature scales coming up. You have a lower fixed point and you have an upper fixed point. The lower fixed point is taken as the melting point of ice at 1 atmosphere. Upper fixed point is taken as the, any guess? Lower fixed point is the freezing point of water. Upper fixed point, boiling point of water at 1 atm again. So on the Celsius scale, the lower one is taken as 0. On the Fahrenheit, it's taken as 32. And on the Kelvin, it's taken as 273. That's the lower fixed points, as you can see. The upper fixed points are 100, 212, and 373. So that's the melting point of, I should have said melting point of ice, not melting point of water, anyway. And the boiling point of water, okay? Now, how many divisions do you have between these two? That's 100, this is 0, therefore it's 100, isn't it? And how many divisions do you have here? 212 and 32. What's the difference between 212 and 32? Hello? 180. So you have 180 divisions here. And how many divisions do you have here? 100. Okay, so can I say that 100 divisions on the Celsius scale is equal to 180 divisions on the Fahrenheit scale? Can I say that?
Yes.
So one division is equal to 1.8, correct? 100, see, many people think physics is about taking notes. No, it's about understanding. 100 divisions on the Celsius scale is equal to 180 on the Fahrenheit. So I'm going to say 1 is equal to 1.8, isn't it? So when you try to change from Celsius to Fahrenheit, for example, if you have 50 degrees Celsius, can you change it to Fahrenheit? I told you, 1 here is equal to what? 1.8. So first you multiply this with 1.8. So that'll give you 90, isn't it?
Yes.
90. And then, because the starting point is 32, you got to add 32. That should be very clear, isn't it? The starting point is 32. So 90 plus 32, how much is that?
122.
Now, if you're changing the other way, Fahrenheit to Celsius, let's take the same number. Can you get 122? Of course, you have to get 50, isn't it? 122 Fahrenheit becomes 50. Okay, go ahead, get 50. Use whatever formula you want. Having said that, how do you change Celsius to Kelvin? You've done that in chemistry many times, everybody knows. You got to add 273 to Celsius to change it into Kelvin. Everybody knows that, right? Okay. So I'm going to write it a little bit different, and I hope you will see, because if I write 9 by 5, that's 1.8. Okay? So when I give you the formulas, we don't need that. Isn't this the formula I gave you? F is 9 by 5 C plus 32, which is 1.8 times C plus 32. And then the other one, you see the difference? First you got to subtract 32 and then multiply with 5 by 9. Because multiplication with 5 by 9 is division by 9 by 5. Okay. And then to change into Kelvin, like I said, it's C plus 273. I'm trying to give some examples there. You can just look at that. An interesting question is there any temperature at which the Fahrenheit and the Celsius scales will have the same number?
-40?
Because you saw it there?
No.
Okay, Paul, you knew it. Okay. At -40. And see how I've asked that as a question once, like 2 points. I've tried to prove it to you another way. I took F as -40, put it into the formula, and I got C as -40. You see that? But that's not the right way to get that, because if I ask that on the exam, like, is there any temperature at which Fahrenheit and Celsius scales agree with each other? They are the same number. How are you going to get the -40?
Yeah, you solve for F in one of them and then set F equal to each other.
Okay, how? Again, let's
All right, for instance, you take your F formula and your C formula, or your C formula, solve for F, and then plug F.
hold on. From this solve for?
That, leave alone. And on your next one, on your C formula,
No.
solve for F.
Start from here again.
You can do it both ways, it doesn't matter.
This is the formula we have. How do we get -40 from here?
That's math.
Make it equal to the C formula?
Make it equal. Okay, I'll write the C formula. So that's 5 by 9 F minus 30. Okay, so what are you telling me to do? What are you asking me to do? I just,
Plug C in over on the left-hand equation.
oh, take this whole thing and write it in place of C?
Yeah, go ahead.
That won't get me anything.
That's what I'm saying. If you solve for F in your second equation,
Okay, get it. I'll give you 2 minutes. what I wrote down there is very important, that there are no negative temperatures in the Kelvin scale. I'm sure you knew that, right? The lowest is 0 Kelvin, so there are no negative temperatures in the Kelvin scale. So keep that in mind. Okay. Now, thermodynamics, actually these 4 chapters are related to each other. All the chapters in heat are connected to each other, and this is where we're getting into, where we start studying about how does the gasoline engine work, what's the difference between the gasoline engine and the diesel engine, how does a refrigerator work, how does a heat pump work, and all that. But we can't jump into it unless you get some ideas. And the basic ideas are, first of all, this word, what does it mean? Thermo means heat, dynamics means movement. Using heat to move. That's what that word stands for. Using heat energy to move. That's what an engine does, right? Uses the heat energy to move. There are 4 laws in thermodynamics. Usually when they name the laws, the first one should be called the first law, second, third, right? What happened here is they got a law, they called it the first law, and then got a law that's more basic. So they had to call it the 0th law. Backwards. So, the 0th law of thermodynamics. I have to tell you, otherwise you look at it and say, what? 0th law? This law just defines a term called thermal equilibrium. Thermal equilibrium. Simply stated, thermal equilibrium means same temperature. That's it. Same temperature. That's all. But why is this word, what's the significance of this word? Same temperature would mean no heat flow, isn't it? If the temperatures are equal, will heat flow? No. So that's why this word is significant. So that's the 0th law of thermodynamics. Let's see how it is stated. That's so slow. It's relating 3 systems, actually. If you have 2 systems like that, A, B, and C, you have 3 of them. If A and C are in thermal equilibrium, B and C are in thermal equilibrium, then anybody knows that A and B are also in. That is the 0th law. Look at that. If 2 systems are in thermal equilibrium with a 3rd system, then they are in thermal equilibrium with each other. Big sentence, but it only means temperatures are equal in thermal equilibrium. That's it. That's the significance. Very clear? Okay. I think I should. I would like to start with a question. Usually I ask this question and students have different answers. I wouldn't be able to give you more time, but look at this. Imagine that the door frame and the door are made of wood. Same material, okay, wood in this case. And the guy who built this built it in such a way that there was a minimum gap between the 2. And let's say he built it in spring. My question is it going to be in summer or in winter that the door has a chance of jamming?
Summer.
Okay, I counted. That was less than 1 second. Between my question and your answer, that was less than 1 second. I was counting. Did you see that? Gosh, I can't believe it. After so many classes, you still don't want to think before you give an answer. Did you think it? Summer or winter? Summer. Finished. Now, because you said summer, you got to argue and explain that to me. Go ahead.
The door is expanded. There was already a small gap, so it filled the tolerance of that gap.
So the door frame does not expand.
Oh, okay. Sorry.
Now that's the problem. It's not just the door that expands, the door frame also expands. Correct? Come on. Now my question is, which one do you think will expand just a little bit more? Which one was originally bigger in dimension? Which one was originally bigger in length?
The frame.
Hold the door frame had a bigger length than the door, correct? Therefore, the door frame will expand just a little bit more than the door. So what's going to happen to the gap in between?
A little bit larger.
In winter, which one do you think will contract a little bit more? In nature, whatever expands more will also contract more. It's just like saying the student who absorbs more will have a greater output on the exam. Same thing. So in winter, which one contracts more?
Door
The
frame.
door frame. So it's in winter that it will jam. So tough to understand that. You know? So tough in our brains. In our brains, it's like, no way! So I'm again telling you, if the original dimension is greater, it expands a little bit more. That's just like saying, if I take two copper rods, one 1 meter long, the other one 1.1 meter long, okay? Two copper rods. I heat them through the same range of temperature. Which one do you think will expand a little bit more? Come on, 1.1.
That doesn't make sense to me because the door jam won't expand outwards. It doesn't really make sense. There's nothing to push the door frame outwards. Literally, the wood would expand.
The expansion, I'm going to make it make sense to you. Expansion depends on three quantities. The change in length depends on the original length. You see that? Depends on a constant. What's that constant? Depends on the material. It's called the linear expansivity. Linear expansivity. Or what's that? Change in temperature. So those are the three quantities on which it depends. Now that's why first I told you, imagine that both are made of the same material. Didn't I tell you that? So I got that out of the place. Then, of course, they go through the same change in temperature. I took that out of place, and then the only factor that's going to affect it is the original length, which is slightly greater for the door frame. Have you got it? Okay, the next question, because I intend to keep you awake. That's my goal every day. Has been. If you have a metal plate, put that silly cell phone away, please. That cell phone from the table, please hide it.
Oh,
It tickles me.
Calculator.
Oh God, no. Okay, if you have a metal plate and you have a hole in it, now this is going to bring up some fireworks too. I've cut out a hole in a metal plate. That's clear, right? And I heat it. What will happen to the size of the hole? Oh, thank you. You've not answered in the first 4 seconds.
It will decrease.
Okay, I heard one answer. I'll repeat the question again. Thank you for holding. Some of you are holding it. Very good. You heat a metal plate with a circular hole in it. What happens to the radius or the diameter of the hole is the question. Clear? Okay, that's the question. Go ahead. Now you can answer.
Decrease.
I heard decrease. I heard stays the same. There's only one more option.
The plate.
One more option, please. Increase. Anybody wants to say increase? You'll say it, okay. So we have all three answers. All right, I'll let you answer this. Now I have a plate that has no hole in it, but I draw a circle on the plate using a permanent marker, right? And I heat it. What happens to the radius of that circle?
Is greater.
Increase.
Thank you. If that's the case, if I cut it out and then draw a circle just on the edge of that circle with a permanent marker, it's still going to be the same. I know it's so tough for you to answer that because you're always going to think the material is going to expand inwards. That never happens. Material always expands outwards. Proof?
How does it know?
Proof? Hold on. Proof? Have you seen horse carts? carts that are pulled by horses? Yes. God, where are we? Goodness. I have to say it that way. Okay. What are the tires made of?
Or wooden metal.
Wood and on. Do you know how they fit that metal on that? The steel ring or the iron ring on that? Actually, in the beginning, both have the same radius. The wooden wheel and the iron tire have the same radius. They heat the iron tire to a very high temperature. It expands. Did you hear me? It doesn't go inwards. It expands. And while still hot, they just place it on the wooden wheel. And as it cools, it becomes such a tight fit that nobody on the face of the earth can ever separate it unless you heat it back to that same temperature. On a second thing, have you heard of, in industry, this is a very familiar term. All right, so what I want to do is this. I have another steel plate, and I want to join these two plates to make some machine or something. So what I do is, there are two holes, and I've aligned the holes, you see. Then I have to take a rivet, which could be steel. In the beginning, the steel plug and this hole, they have the same radius. So it won't go in. Are you listening? So I have to cool it. And the best way to cool it is to put it in dry ice. You know what dry ice is? Solid carbon dioxide, right? It's very low temperature. Put it there, cool it. As the metal plug cools, you know, its radius becomes less. And so while it's still cold, put it in. Let it go back to the room temperature. That's the tightest fit ever. Well, of course, you could have done it another way. Instead of cooling the steel plug, you could have heated both the metal plates, which is considerably tough in doing. And it's a waste of energy. You know what I mean? Because that's so much bigger, you're trying to heat everything. So usually what they do is just cool this, you know, and take it and put it there. That's what happens. Expansion has so many applications. Goodness, the picture here shows you the gap that they have to have in a bridge. That's an expansion gap. Because in summer, as it expands, if you don't have space, it's going to buckle, isn't it? And think about something like the Golden Gate Bridge, which has, what's its length? About 3,000 feet. 2,700 something feet. And do you know how much it's expanding in summer? It expands up to 3 feet. That's not a small amount. That's one, right? So 3 is something like that. Therefore, they have all these provisions there. And on top of that, they have one end of the bridge set on rollers so it can move. But don't you think that you and I can move it? No. And if you do not give that provision, the stress will be so high. Has anybody heard of stress? But not in life. In physics. Have you heard of stress?
Yes.
Do you know that it's related to Young's modulus by this formula? And today, didn't I tell you that the change in length, it's still there. The change in length, when you heat it, is, right, that. So can't you first calculate this using this formula? Come on, and put it back into this. Now, wouldn't you be able to calculate the stress in the material if you make F by A the subject? You know what I'm trying to say? That's called the thermal stress. The stress created due to change in temperature. And thermal stresses are huge. If you don't let the material expand, like think about railroads. Have you seen that they have gaps between the rails? Of course. Otherwise, you would have every train derailing and all kinds of stuff because the engineer did not think about that. Okay, so I've thrown like 4 applications at you. Let me show you another application. What you see here, right here, is called the bimetallic strips. It's 2 different metals. You see that? 2 different metals. And so they have different expansivities. And so if it's heated, can you tell me which one of these has a greater linear expansivity? Because it has bend. Do you see that they are fixed together, so they can't separate? So you can see how they bend.
The one on the left,
Use the colors, please. Yeah, surely blue has a greater expansivity, isn't it? You- Well, I can't explain that if you didn't get it. I can't. This is simply called a thermostat. How did you think the refrigerator switches on and off by itself? How did you think the automatic iron switches on and off itself? When you set it at a particular temperature, when it reaches that temperature, what happens is it switches off, right? And then when it cools down, again it switches on. It's because of a thermostat. It's because of a bimetallic strip. What you need to do is just have an electrical connection here. I mean here. You see, let's imagine there was something touching here. And so here there is a contact. And so there's an electrical circuit here. That's what I'm trying to say. But when it heats up, that point is here, isn't it? Is there an electrical contact now? Nothing. No current flowing. No heat is produced. But as it cools, again it straightens. You see that? And then it touches. This happens a million times. That's how temperatures are controlled. But there are other ways in which temperatures could be controlled. This is one way of controlling temperature, okay? Okay, please keep the questions till the end because I want to just finish. I'll give you all a chance. Otherwise, we're never going to finish. Okay. Alpha, did I tell you that alpha is called linear expansivity? But there is another problem now. If I have a steel plate, there's no sense in talking about change in length. Now, what do I have to talk about? Change in
Area.
All right. So if I'm going to calculate change in area, I'm going to have to use the formula change in area is equal to original area times 2 times alpha delta T. Common sense, because there are 2 dimensions, it's 2 times alpha. See that? Got it? But what if I have a cube? Now I have to talk about a change in volume, and therefore the change in volume would be the original volume times 3 alpha times delta T. Now 3 alpha, now this formula is a very important one, change in volume. You know why? Because liquids and gases have nothing to do with change in length. What do you mean by change in length of a liquid or a gas? No sense. It has nothing to do with change in area. So this is one that's applicable to all solids, liquids, and gases. Therefore, this constant, 3 alpha, is also called beta. It's called cubical expansivity. So I'm trying to tell you that cubical expansivity is 3 times alpha. That's what I'm trying to say. So in a problem, let me not trick you. If I give you the linear expansivity and I'm asking you to find the change in volume, you got to use 3 times alpha before you plug it into this equation. That's what I'm trying to say. But sometimes I've given cubical expansivity. People don't read. They'll multiply that with 3 again. You heard me, didn't you? If I give you cubical expansivity, why should you multiply it with 3? So you have to read the problem. If it's linear expansivity, multiply it by 3. If it's cubical, just use it. So volume expansion, that's what I just talked about, and that's everything there on the screen. Change in volume is original volume times, you can also call it the coefficient of volume expansion. You see that? The coefficient of volume expansion is cubical expansivity. Simple things. That brings another question to my mind, because remember, my goal is to keep you awake and thinking. We may have studied a lot of material during the semester, but my goal has always been to make you think. Remember that. Not just cram the material. Okay, here is a question that I had asked one time. To measure temperatures, we use thermometers, right? And haven't you seen a thermometer? Of course you have. The most usual one is, well, nowadays you have digital thermometers, but I'm talking about the olden days when we had the mercury in glass, right? Why do we use mercury? There are many reasons. Number one, mercury does not stick to glass. Most important. Because if it sticks, it won't move. You see that? And we want it to move. Mercury can be obtained in a very pure form. And is mercury a metal? Therefore, its linear expansivity is high. You heard me. So if you use mercury, you have all these three advantages, and it's more sensitive. It expands a lot more. So now, sometimes we also use alcohol in glass, and it's given a particular color, reddish. You've seen it, right? Alcohol in glass. So this is a problem that I asked. You're trying to measure the temperature of something, and when you first put the alcohol in glass thermometer into that something, the alcohol level goes down instead of going up. It goes down, and then it shoots back up. Would you be able to give me the reason? Wow. Goodness, you've not talked for 7 seconds. You're thinking. Yeah, I got it. You got the question? When you first put an alcohol thermometer into something hot, like, let's say, soup, and you want to measure the temperature, if you got the answer, hold on for some time. Let's make others think. Matthew, I'll give you a chance. I'm sure you got it. Okay, so first, the alcohol level goes down, and then it goes up. So don't give it out. Let's make others struggle a little bit more because, but I know that's not a good picture, but you know what? Don't laugh at my pictures. Come on. Now, if it was originally here, it goes down to B, and then it shoots up to C. You know what I'm trying to say? Why is the reason one hand has gone up? And I'm going to give you 30 seconds more. Not even one more hand, it's only, okay, second hand has gone up. So after I give you notes, you go back home and study that and give me the answer. That's not going to make you a good engineer. Because there are going to be questions out there that nobody's ever answered. And you got to figure it out. I'm telling you. No textbook is going to give you the answer. Because it's a particular question, and it's specific to that situation. You know what I'm trying to say. And you can't ask anybody else. You're the chief engineer. You have to sit down. You have to think. Matthew, I'll give you the first chance.
I think it's because it's going to heat the glass up first.
And so?
And so it's going to put pressure on the alcohol, and the alcohol is more sensitive to the pressure.
Okay, I'll see whether Richard has a different answer, and then I'll come back to you. Yes?
Is it because the rate at which the glass expands is faster than the rate at which the alcohol?
Okay, so I heard a second version. No? Okay, now I'll come back to, I saw another hand somewhere. No? Both of these are correct partially, but I'm looking for something. Now, let's start from Richard. Richard said the rate of expansion of glass is more than that of alcohol is wrong.
Yeah,
Liquids expand more than solids. Okay, now Matthew said when the glass expands, it puts more pressure on alcohol, something to that effect. Actually, the pressure decreases because the bulb expands. That means the bulb becomes greater in volume. That's why the liquid level drops. Simple. The heat first gets to the glass bulb before it can get to the alcohol. Do I have to prove that? I can't. You just have to understand. Because the heat has to go through the glass into the alcohol, right? So the glass bulb gets heated first. What happens to its volume? Increases. When its volume increases, by that time the heat has not even reached alcohol. Are you listening? So down, and then by that time the heat reaches alcohol, so it expands much more than glass. So technically, your actual expansion of alcohol would be AC or AB or BC. What's your actual expansion of alcohol? how much did alcohol actually expand? Huh?
BC?
BC, thank you. How many understood that it's BC? Correct. But you would only see AC. You know what I'm trying to say? Because you would see it at A, because A to B is temporary. You know, it just, if you're not watching carefully, you won't even see it, you know. You will look at A, you'll sing a song, when you come back, it's gone to C. But in between you, what happened? A went down to B. So if you're going to measure accurately using an alcohol thermometer, you're going to include this as my God. You understood? Did you understand? Everybody did. I think I should give. That's not true. Water is special in so many ways. Wow, water. One speciality of water is you cannot commit suicide by jumping into water at noon during summer. Why did I say that? Well, because the temperature of water does not go up at all compared to other liquids. What liquid do you use in a radiator of a car? What liquid do you use in the radiator of a car?
It's mostly water, but.
Mostly water plus anti-corrosive thing, which we really don't need in Texas, you know. Anti-freeze, I mean, you don't need in Texas, you know. It's never going to freeze. Last time I heard about freeze in Texas is 100 years back. Anyway, never mind. So you don't need that. Yeah, no, I think in 2008 it did snow. Was anybody here?
Yeah.
2008? Oh,
Hey, we had some flurries this year.
okay. Anyway, coming back, water is so special because it has what's called anomalous expansion. That word anomaly means special, extraordinary. It's not like other liquids. Wait. What happens to other liquids when you heat them? When you heat a liquid, what happens to its volume? Expands, correct? But if I say that you heat water and its volume is going to decrease, you're going to be surprised. But that's what happens. Not all the time, but between 0 degrees Celsius and 4 degrees Celsius. Did you hear me? Between 0 and 4. So if you take ice, it's at 0. You melt it. We'll talk about the melting later on. And you get water. The water is at 0 degrees Celsius, isn't it?
Yes.
It has a certain volume. You start heating it. Instead of the volume increasing, it's going to decrease. All the way up to 4 degrees Celsius. The volume will go up. Will go down. After 4, it'll behave like any other liquid. After 4 degrees Celsius, yes, its volume will increase. And so I have a graph, I think I have a graph that makes it clear. Take a look at this graph. Temperature on the x-axis and volume on the y-axis. And that is 4 degrees Celsius. Okay, let me stop it there. Do you see that? Can you even touch this now? Do you see that the volume has gone down? And although I didn't label it, here it is 0 degrees Celsius. This is 4 degrees Celsius. Okay? So from 0 to 4, the volume is going down.
It's not similar to melting point of depression, is it?
No, that's something else. Okay, and then beyond 4 degrees Celsius, it behaves like any other liquid. The volume keeps increasing. So can I say something and tell me whether it's true or false? Water has maximum density at 4 degrees Celsius. Okay, let me try this. Water has minimum volume at 4 degrees Celsius. Oh, you won't even agree with that?
Yeah.
And density is mass by volume. So if the volume is minimum at 4 degrees Celsius, then definitely the density is maximum at 4 degrees Celsius, and that is what we call 1,000 kilogram per meter cube. So it's the maximum density of water that is 1,000 kilogram per meter cube. So we're not technically correct when we use 1,000 at room temperatures. It's got to be a little smaller than that, but negligibly smaller. But this has another beautiful application. You know, human beings are selfish. That includes me because I'm a human being. And you know, if we heat up our homes and cool it using air conditioners, but think about a pond of water. A pond of water. And it's freezing cold. It's been freezing cold for, let's say, 10 days. So the outside temperatures are like negative 15 degrees Celsius, okay? What's going to happen? Think about this. What's going to happen? The water's going to freeze, isn't it? Now, two things. This is one reason why I don't believe it all happened by chance. Which part of the pond begins to freeze? Thank you. And when ice is formed here, ice will continue to stay on top because ice has a lower density than water, correct? And remember that ice is a very bad conductor of heat. We're going to come to that topic later on, but I just want to connect. It's like a blanket. So the rate of freezing of the water down here decreases because to freeze, the heat has to escape through the blanket of ice. Are you with me? Ice is a bad conductor of heat. And so the rate slows down and slows down and down. It will get thicker, but very slowly. And the more thick it gets, the tougher it becomes for the heat to escape. Now, add on to that the idea that I just gave you. Water has maximum density at what temperature?
4 degrees.
So if you look at the temperature of water here, it will be 4 degrees Celsius. The organisms are safe. We would not have provided. What's the temperature outside? Negative 15. On the surface of the pond, 0. What is at the bottom? 4 degrees Celsius. All of this happened by chance. Good luck with that. All right, thank you. Because we would not have provided a heater. We would not have provided air conditioning or whatever. We are selfish. Nature has provided its own. And it just happened by chance. All right. So you got it.